let me thank the organizers for the opportunity to present this here. I will talk about many things related to what Bruno was talking about, and since he gave this really nice sort of holistic view of the story, I think the talk that I will give now will be even more understandable than it would have been before. And the main idea or the main theme in this talk is that of Poincaré-Birkhoff-Witt theorems in the sense of the classical one, and how sort of the operatic calculus can organize the idea of what a Poincaré-Birkhoff-Witt theorem is to other situations. Okay, so let me remind you what exactly this is. So the original sort of classical PBW theorem just says that when we have a field of characteristics 0 and we take a vector space underlying some universal enveloping algebra of a Lie algebra, so for example, I take the universal envelope of SL2, for example, then that will be isomorphic as a vector space to some symmetric algebra. In the case, for example, this is 3-dimensional, then this here will be just polynomials in 3 variables, right? And not only we have an isomorphism, but that isomorphism is natural. It's natural with respect to Lie algebra maps, okay? And why is this important? I mean, you may have bumped into this theorem in different situations. If you want to study the representation theory of Lie algebra, this understanding this object is important because it's important to computing cohomology. If you're doing homological algebra, perhaps in a broader sense, and you want to compute Hochschild cohomology instead of Lie algebra homology, then, well, actually there's a relation between the two, but you also need to start doing something with this algebra and trying to study a Koszul complex and things of the sort, and the symmetric algebra pops up there immediately. And if you're thinking more of perhaps quantum situations where these Lie algebras are perturbed, then, well, you're dealing with PBW deformations and some quantization ideas. So you may have bumped into this result. I think it's reasonably famous. So as I was saying, there are sort of many results perhaps that fall between this PBW umbrella. There's a very nice survey by Witherspoon that explains, for example, that one of the ideas of this PBW theorem is to indeed exhibit an algebra as a deformation of another algebra, which is kind of nicer in some sense. Like, we need to specify what we mean by nicer. Second, part of the reason why we think the other algebra is nicer is because it has some sense of canonical forms. So the polynomial algebra, it has canonical forms that we can compute with. And finally, from a point of view of organizing things, it produces something graded for us. And if you've done, kind of homological algebra with graded things behave better, right? So it's kind of nice to be able to associate graded things to ungraded things, or, well, they're ungraded but filtered. And our motivation, and here's where perhaps operads will start to pop up, is that we wanted to formalize this idea in a way that we can prove new theorems. I mean, at least myself, before writing this paper, I knew about the PBW theorems for associative algebras that are non-commutative in the sense of Posicielski and Polishuk, in the sense of perhaps the book of Bruno and Jean-Louis Loday. So when you take quadratic versions of operads and you have some kind of PBW theorem. And, well, we wanted some general picture of what was happening. And when I say we, I mean myself and my advisor, Vladimir Dotsenko. So there's kind of a precursor to this whole idea of PBW theorems that does not quite involve operads yet, but it's almost there. And it doesn't really involve higher structures perhaps yet, but it's work of Mikhailov and Shestakov, where they thought of just having a class of algebras of one time, that's what they call varieties of algebras, and a class of algebras of another kind. And what they want to do is think that they have a functor that changes an algebra for another, for example, an associative algebra for its associated Lie algebra, and think of its left adjoint. And they have a notion of what it means for this left adjoint to be a PBW pair, they call. But still, their result is sort of stated in terms of having a basis of normal forms in the associated grid object, and we weren't happy with that. We wanted something kind of coordinate free. So exactly what the question that I want to answer with this sort of ideas coming from perhaps homological algebra and operads is, what does it mean precisely to say that this universal envelope does not depend on A? No, and in the case of PBW, it says that no matter what Lie algebra you give me, if it's abelian or not, things doesn't matter. If its operations are 0 or non-zero, the universal envelope is quote unquote the same.
So
and for us,
may I ask a question about the last thing? So what is it? S and T? They are operads, right?
No, they are sort of varieties of algebra, so defined by equations, right? Like the class of, I mean, it's kind of a different way to present the theory, but you can think of SST as monads if you want.
Okay.
For
so
me,
these
I
are
think of them as
monads, and these are algebra services monads. So S and T are monads.
Yeah.
Okay.
Yeah. I mean, they do not use that language in this paper, but it's the language that I like to use. Yes, that's why I said T algebra maps here, precisely. Now I will come back to this definition, but mimicking what happened with the PBW case, I want to say that the sort of underlying object to this functor here is sort of naturally isomorphic to some functor on the underlying object, and this functor x doesn't have to depend on the input I gave it. I gave it as an algebra, just as a vector space. So essentially, one can arrive to a result fairly quickly, and then one knows the intuition from the result from associative algebras, for example, and then one can build a final result in greater generality for monads. Okay, so let me just explain to you more or less what's happening, and then I'll sort of break down the details and explain how perhaps we want to use it for operads. So the language we choose. So now, as Boris was saying, we will try to change the language for something that we like a bit better, which is monads. So in our case, the monads will be operads. Operads have their algebras, so we want to say something about a map between operads. So what we will do is we will focus on functors that arise from a morphism of operads. So as Bruno was explaining, when we have operads, perhaps this was not morphisms of operads appear as resolution in his talk, but in general, if we have a map of operads, whenever we have an algebra over the codomain, well, we can pull it back to an algebra over the domain. Now, for example, a commutative algebra is always an associative algebra. An associative algebra is always a Lie algebra. A commutative algebra, if you know what it is always a permutative algebra. So whenever we have a map from one operad to the other, we can pull back the structure. And then this pullback functor, I'm not thinking of it in an abstract term as above, but I'm thinking that it's concrete and it comes from a morphism. Second, once things are presented in this way, this left adjoint, and you may know what this notation stands for, it appears as a push forward, meaning if I have a Lie algebra, I can push it forward to an associative algebra by universal envelope. If I have, in other situations, if I have, for example, I mean, in the case of associative envelopes, you know, if I have an associative algebra, I can push it forward to an algebra whose well, left modules are bimodules. So there's a dual notion of pulling back that is sort of inducing representations, right? Sort of, and that is that left adjoint. And then what I will explain to you is that this push forward functor that appears here is nice precisely when some homological condition holds. And here is when I will not only be doing calculus with operads in the linear case, but also doing some homological algebra in the middle. Okay, now let me sort of back down a bit from the whole complexity of the situation and try to break it down into pieces so that we can appreciate what's actually happening. But before I do that, what I want to tell you is why this is useful, because, well, I will introduce a few notions, a bit of notation, and I want to sort of convince you that it's worth the while. One of the reasons why we like to pass from sort of computations with algebras to computations with operads, and perhaps the point was already done by Bruno, is that with operads, we can explain in a completely general way what happens with our algebras. Now, for example, A-infinity algebras, well, they are algebras over the resolution of the associative operad, and we have A-infinity algebras and we have transverse theorems because that is the Kosuo model of the associative operad. So there is a single object explaining a whole homological phenomenon in a whole category all at once. Second, perhaps this was not something that Bruno mentioned, but there are methods to study operads. So once I identify an object that controls the theory that I'm studying, one can start to poke that object with the theory and try to say something. And there's things coming from Grobner basis that you may have heard. And then there's a bit of homotopical algebra, as it was explained by Bruno. So sort of taking this step back and changing our vantage point makes available tools that are really useful, and we wouldn't have been able to see them before. Then the third reason why doing this is useful is that this approach is kind of intrinsic and functorial, meaning that when I say intrinsic, it means that it does not depend on the algebra that I'm working with. So I don't have to choose, for example, a basis of the Lie algebra to state the Lie theorem. And also it sort of explains this sort of mystery. Okay, why really, in the case of the Lie and the associative operad, there is a PBW theorem? What makes it work? Okay, and explaining why it works allows you to actually deduce how, when I have a general situation between two operads, I can actually construct homology classes that sort of would explain if our wish is obstructed in some sense. And finally, perhaps in a more broad sense, it does explain why in positive characteristics things doesn't work, and this has already been explained in the previous talk. In positive characteristics, the symmetric groups are homologically bad. We need to resolve them, so it's hard to expect that homological algebra will not change when we pass to positive characteristic. Okay, so let me tell you what this Poincaré-Birkhoff-Witt property is by telling what its objects are. So, well, Bruno has already defined an operad as some object with these compositions. I want to think it as a monad, so I'll think of it as what's called a sure endofunctor. A sure endofunctor is a sequence of representations of the symmetric group that I encode in this functor, right? And in general, we're taking vector spaces or chain complexes or graded vector spaces, and our functor takes this very perhaps Taylor-looking form, right? There's a Taylor expansion in the variable b. So having an operad means that we can actually apply the functor again to this, and there will be some compositions appearing between, let's say, PA and PB now, that make this functor into a monad. So that's this composition law that appeared before. In general, we're interested in symmetric operads, but there are non-symmetric operads. There are, well, colored operads, non-symmetric colored operads, and one can sort of develop this formalism with the level of generality that is necessary for your applications. Now, once I have monads, in this case, operads, I have algebra. So Bruno explained that, for example, the infinity operad has as its algebras the infinity algebras. Of course, we have the Lie operad, the commutative operad, and they all define a theory. So an algebra over an operad will just be a map, what's called a structure map, that takes elements that look like composition schemes. So this is a tree that I decorated with elements of V and returned for me an element. So the actual concrete way that we like to think about it is that every element of my operad, as Bruno explained, gives me an endomorphism, a multilinear endomorphism corresponding to the number of leaves that my tree has, right? So I have my algebras, okay. And as an example that perhaps now is kind of a bit more trivial than it would be if we didn't have the talk before. Well, if we have the trivial representation here, we're symmetrizing this vector space. So this equivalent operations will be completely symmetric, and we can actually cook up the commutative operad as just a sequence of the trivial representations. The composition maps are sort of uniquely determined, and that gives for us the theory of what it means to have operations on symmetric monomials, okay? Very well, so once I went from monads to algebras, I can also go from morphisms between operads to this envelopes that I'm interested in. So if I have a morphism of operads, as I was telling to you before, there's a pullback functor. Whenever I can act on an algebra on the codomain, I can pre-compose with that morphism, and I can act on the algebra seen as a p-algebra. And of course, as I was explaining before, this pullback does not change the underlying object. It sort of remains intact with it, but it changes the algebra structure. Okay, so as an example, to introduce some jargon, this is called the universal enveloping functor of our sort of context here in the case of this morphism, and it exists in general. So we have to do some careful, we need to look at our underlying category carefully, but if it's vector spaces, chain complexes, symmetric sequences even, this push forward makes sense, okay? You just need to take a free object and quotient. So if you have co-equalizers that behave nicely, you can work. And as kind of the example that we have is that there is a map that includes the Lie operad into the associative operad and gives a map from Lie algebras to associative algebras. That is just the inclusion, right? We can take brackets of elements in V and they live inside the tensor algebra. And if we follow the definitions of what it means to compute the left adjoint, you will see that precisely this left adjoint computes this universal envelope. Okay, so just small observation that this indeed is just a general setup that we had before. Okay. Now,
so next question. So this is associated with a map of operad Lie to the operad assoc, right? So the right adjoint functor. So
yes.
Meaning that for any associative algebra, you can consider as a Lie algebra with AB minus BA as a bracket. Is it correct, right?
Correct. Yes,
and,
that's
and then
absolutely
you
correct.
consider the left adjoint to that functor, right? So yeah, and then
yes.
you say that you get the universal enveloping in this way of a Lie algebra.
Exactly. So we have the inclusion of operads like this. This is just this evaluated on an element.
Yeah,
so I evaluated this, and this map, if I compute this on a Lie algebra, I get, well, I take the free associative algebra on the underlying element of G, and then I egalize the sort of fantasy commutator with the real commutator, right? That's what I need to do. I co-egalize it, I suppose. So that's how we compute this. So in general, the general idea is that if I have an algebra here, let's say A, then it has some real operations coming from P, and then the free algebra has some quote-unquote fake operations that are sort of this ones here. And what I'm saying is that I'm egalizing them I want to say Q, and I'm egalizing them in the quotient. That's what I'm doing. Yes.
Thank you.
So the whole point of the sort of the framework that we developed with Vladimir is to control this. So basically, how can we use the idea of going back and standing on the sort of floor of operads. There's sort of this this analogy in the work of Hinich where he says that one works at the three levels: monads, algebras, and representations. So by standing at the third level, one can organize these computations done at the second level in some sense. And the only sort of extra definition that I need to give you is that I need to work with sort of more rich objects than just algebras. If I have an operad, P, then I can consider, well, another symmetric sequence, like, let's say, M, N, like so. And I think I recovered now the use of this, or if I look, there you go. Sorry, my mouse was frozen on my screen, but I see that it moves on your screen. So the last notion that we need is that of a right module over an operad. So operads have algebras that are sort of things that are obtained by composing them here on the right. But for our purposes, we need to sort of compose things on the left and act by them on the right from P. So it's just the equivalent of what a right module is for associative algebras for operads. Okay, it's a bit more complicated, but it means that on every tree that I have on M, I can feed trees of P on the roots. Okay, so whenever I have a diagram that has an element of M at the bottom, and I have a collection of trees that I can insert, this will define for me, oh, this is an M, a new operation of M, or just a sequence, an element of M. Okay, sorry, that P has to be an M, of course. Okay, and finally, the last, perhaps here is where sort of the first homological algebra appears, is that a right module, as you know, is free whenever it sort of appears as a left adjoint, and I think this F should be a P too. So whenever it appears just as the, I suppose, left adjoint in this case of applying a free functor. So free modules are just the ones that are obtained by tensoring with your algebra over some underlying space. Okay, so let me just do a checklist here. I have operads. I want to control their algebras that I think I wrote with a little c, so these are P algebras. And finally, the last notion that I will need is working with right P modules. So with these three ingredients, I can tell you precisely what the sort of bare bones statement of a Poincaré-Birkhoff-Witt theorem is. So that statement, and let me recall that, well, the PBW property holds for us, that's our intuition, whenever this functor is constant and represented by some constant functor on the underlying algebras, and once this sort of definition is given, one can recast it in terms of the whole operatic machinery. So the theorem that one can prove is that a map of operads, or more generally monads, has this nice PBW property precisely when the target operad is free to the right over the domain operad. And not only that is an if and only if, but actually the functor x, sorry, is recovered if I find a basis. So not only can I state when this functor is nicely behaved, but also I can find the functor sort of representing it in a nice way as a basis of Q. Okay.
So last question about your notation in before above the theorem statement. So then this sharp sign, or how you call it, so it's underlying object in vector spaces, right? So then you are saying that. So then the right adjoint, you take right adjoint of A, and then you take the underlying vector space, and then it should be isomorphic to X. Right, of A. So it means that it depends only on the underlying vector space of A. This is the idea, not on the algebra structure on A, but underlying vector space A, correct?
Exactly, yes.
Oh, thank you.
Exactly, yes. Sorry, I always forget to say what sharp is for me, and I always get this question, and I think I haven't learned from that. Now, the thing that I want to say is that the proof of this theorem is easy, and I don't mean to say this to sort of remove any merit from the theorem, but I want to say that what's important is not the result itself, but what you can do with it. So there's, if you have taken, for example, combinatorics or things like that, you know that there are some tricks in combinatorics that you can do. For example, you can count the objects of a set in two ways, and then you get the Burnside formula for group actions, no? And that's a really cool formula to prove results. Or you can use the pigeonhole principle, which is the most like tautological statement in the world, and then you can actually prove a non-trivial combinatorial fact. So in this case, this theorem kind of plays that role, that from a point of view of proving it, it's easy, but it sort of opens the door to being creative with it. So how can we apply it? Basically, sorry, let me go back. Basically, we need to find useful ways to proving that something is free, right? I mean, if I want to apply this theorem, I want to be able to tell when an object is free as a right module. So the question is, when can I do this, or what machinery do I have? And well, we have the whole machinery of homological algebra that exists almost for like 60 years now. So there's something that I sort of call a homological hammer, which is kind of a version of something you may know as the Nakayama lemma in even commutative algebra. Now, in commutative algebra, you know that, let's say if you have a weight-graded algebra, and you take its sort of augmentation, so this is sort of A over this, then whenever you have a graded module and you tensor it with K over A, and you get 0, then, well, if M is non-negatively graded, or it starts at some point, this means that the module is 0. It's sort of an induction argument in the degrees. And there's an equivalent for homological algebra that replaces the tensor product with the derived tensor product, and the conclusion is not that M is 0, but that M is free. So there's a complete analog of that for operads, and here's where I'm sort of using some operatic calculus that says the following. If I have an operad that is weight graded, for example, the associative operad is weight graded, the Lie operad is weight graded, the commutative operad is weight graded. Most of the operads that appear in nature are graded by just the number of operations its relations uses. And if I take a module that is also weight graded, then, as I was saying, the module is free if and only if this is 0. And this thing here, you can write it a bit more in a more readable way as this. Okay, so
the bar is the bar resolution, sort of bar resolution,
yes,
right?
Yes. So if for those who know, this is the bar construction, or the double-sided bar construction. You may have seen it for algebras, and again, as Bruno was explaining, there's a completely analogous theory for operads. And moreover, so this statement of freeness holds if and only if the homology of something is acyclic, and what remains in degree 0 is actually the basis that we're looking for. So what this theorem says is that if you want to compute, if you want to decide whether a PBW theorem holds in the weight-graded situation, you can actually produce a complex and compute its homology. And if its homology is non-trivial in some higher degrees, you're out of luck. And if its homology is acyclic, then what remained at the end of your computation in degree 0 gives you actually the solution to your PBW problem. So as I just said, well, the main takeaway is we don't need to think, we need to compute, right? And then whatever pops out of this homological machine will tell us what the answer is. So let me give you an example of how this machine works in the classical case. So as we were saying before, there's the associative operad that was discussed before, the Lie operad, and I can map its bracket to the anti-symmetrized version of the product. And what this is saying is that, well, this thing here is a Lie bracket. That's why I can map one to the other. And this map gives rise to the universal envelope. Let's call this C as before. And we want to know if a PBW theorem holds and what the module is. And I claim that, well, of course it does. And the proof goes as follows. So what I will do, and I think the other proofs are a bit more organized instead of just a block of text, but I will take the associative operad. And I will filter it. So whenever I take an associative product, I can break it up. I can break it up into a symmetric version of it, which is not associative, and a bracket. And so when I iterate this operation many times, there's some amount of times that I use the bracket, and I will count it, and that gives me a filtration on this operad. And now if I compute the graded module that I get, you can check that it's the module controlling Poisson algebras. The reason why this happens is that this thing here is not commutative, but it's commutative up to some brackets. So when brackets are killed in the associated graded version, we get something that is actually commutative, and now this and this behave like the Poisson operad, right? A Poisson operad, a Poisson algebra is an algebra with a commutative product, a Lie product, and then a Leibniz rule. Okay.
Sorry, but here you also using, to perform this computation rigorously, saying that as is a free Lie right module, right? You also need sort of universal Poincaré-Birkhoff-Witt theorem, right? When you describe,
No, please go ahead.
So that if you like to ask a question, so what S is a right Lie module, right, in the operatic sense, it's also sort of what you are doing now actually for this proof. That a sort of Poincaré-Birkhoff-Witt theorem, maybe in its universal form in a sense, is hidden there, no?
Yes. Basically, that's what I want to argue, that the universal form of the PBW theorem is codified in this equality, precisely.
Right, yeah, so it's not a proof in a sense, right? If you like to, that you have to prove that one.
I don't need the PBW theorem to prove this. You can actually prove it in I can tell you a proof that does not use PBW. That I know, but it's a bit far-fetched. And then what I do is take the associated graded, and I was saying it's Poisson. And as we were just discussing now, well, the Poisson operad is kind of, it's more obvious that it's free. Like you can argue that it's free more or less by the shape that it takes, because the Leibniz rule says that commutative products can be put below and Lie products can be put above. So Lie operations can be put at the top, and then this exhibits the Poisson operad as this composition. Okay, so and because, well, I took something whose associated graded is free, then I wave my hands and I say spectral sequence argument, and I deduce that the associative operad was free and with the same basis. Okay, and then what this says is that this sure endofunctor, which is precisely a symmetric endofunctor, gives me my PBW theorem. Now, again, this version of the PBW theorem is a bit more trivial, but well, let's think about more difficult situations. So when did we start? Because I'm a bit worried about time. I think
we started at like 22 past. So
right. So about half an hour has gone through. Okay, no, I think we're good. Okay, so let me tell you another story. So there's a class of algebras called Prelli algebras that I'm not sure if Bruno mentioned, but they are quite important because they appear very naturally when one does, for example, the formation theory with operads. In some sense, the formation theory of operads is not controlled by Lie algebras, but actually by Prelli algebras. And there's a very beautiful paper that's called Prelli deformation theory that actually explains how that works. It's Bruno and Sergei Shadrin and Vladimir Dotsenko. So okay, these Prelli algebras are defined by one single operation that satisfies a particular condition, that its associator is symmetric, and it appears, for example, when you compute Gersten-Haber circle products, and again in deformation theory. But the insight of Gersten-Haber from many years ago is that its anti-symmetrization happens to be a Lie bracket again, and that's why it's related to like Lie deformation theory. What this means, as before, is that there is a map, and I didn't write that, but there is a map from Lie to pre-Lie. And one can wonder if, again, if the universal enveloping pre-Lie algebra now of a Lie algebra is nice enough. And the answer is that it is. And now the functor changes a bit. You need to compose two functors. I won't explain exactly what R is, but I'll leave it here. It's some endofunctor. You can read about it if you'd like, but now I want to focus on the fact that it's actually nicely behaved. So how do we prove it? It's kind of similar. So we will polarize again the pre-Lie product into a symmetric part and an anti-symmetric part, and I will count how many times I use the anti-symmetric part. And then there's a very nice paper of Vladimir Dotsenko where he actually computes the associated gradient. It's defined by an operad that controls certain algebras associated to geometry. This operad is a bit unwieldy. It is not quadratic, for example, so it does not fall within the whole Cauchy duality theory, but it can be studied, and it was studied by Vladimir in this paper. And one can show that, well, this operad that was obtained, that is called the operad of manifold algebras, has a basis. So it's even as a span, it admits a certain basis of trees that, again, as in the situation of the Poisson operad, sort of happen to have the Lie trees on top. And that means that when I start inserting more Lie elements, I will create the same basis elements, which means that the thing that does not have any, the things that do not have any Lie product are a basis, as before. No, it's sort of I sort of need to what do you call it? And you need to sort of trim the trees and remove the Lie part at the top, and whatever remains here, which is not so easy to pin down in this case, because again this operad is a bit more complicated, gives me a basis. And again, by this sort of spectral sequence argument, the pre-Lie operad itself is free. Okay, now again, in this case, the determination of what the endofunctor is was not done by us. It was done in a subsequent paper by Dotsenko and I suppose he's actually an undergrad student, perhaps he's doing his master's now, where they actually, instead of using the bar construction, they use a Koszul complex to compute the homology. And because they can use a Koszul complex which is smaller, they actually managed to identify the homology on the nose. It's a really beautiful computation using ideas from trees and vertebrates and things of that sort, going to like ideas of Joyal. Okay, now there's another situation. I didn't want those relations to appear, so ignore these relations for a minute. But there's another class of algebras that were studied by Jean-Louis Loday that are called dendriform. Now, these are even more complicated and exotic, perhaps, than pre-Lie algebras, but they appear in some context which I won't explain perhaps now, and they have two operations. And these two operations, now that we can look at the identities just for fun, but I won't really use them too much. It's sort of their associators in different ways that we can compute them are either non-associative up to some combination of them or happen to be associative. So there's two relations that behave in some way, but they happen to satisfy the condition that when we anti-symmetrize them again, we now get a pre-Lie algebra. And not only that, but if we take the symmetric part, then we get something called a Zimbiel algebra. And again, here we're entering the realm of exotic sort of operads that satisfy certain again, its associator is equal to something else. Doesn't matter what that is. But what that means is that again, we can sort of map the pre-Lie operad into this dendriform operad. And Jean-Louis Loday, he wanted to know if the universal envelopes of pre-Lie algebras that give dendriform algebras are nice in some way. And again, the reason why one may want that to be true is because, again, one can study the homology of dendriform algebras using universal envelopes. So, well, it would be nice if one had a PBW theorem. And we managed to show that the answer to that is yes, there is a sort of PBW theorem. So how do we prove it? And you'll feel like this is sort of a one-trick pony situation thing, and it sort of is. But one can sort of polarize. One can take this dendriform operad, and as before, polarize these two products. And this, let me just note that now that the polarization sort of does this minus that, and this minus that. Okay, it's plus that, sorry. It's a little bit different, but it works. Okay, and if one computes the associated graded module, you actually get an operad that was studied by Marcelo Aguiar, which is kind of a non-commutative analog or a pre-analog of the Poisson operad. So it was defined by him, and it's sort of a non-commutative version of pre-Poisson algebras whose classical limit give it's sort of the classical limits of Preli algebras give pre-Poisson algebras in some sense. This is something that was explained by Marcelo. And again, one can study this pre-Poisson operad in terms of Grobner theory, and one can exhibit a really nice basis of trimonomials that shows that sort of very, very much obviously it is free. And then again, sorry, I move my hands in the air and I deduce that this operad is free with the same basis. In this case, we actually didn't compute the basis explicitly. We just argued that there was one. And that is sort of a pending thing to do. So what can we do with these three results? A question that I was asked when I was talking about this in other seminars was, do you have examples where you don't polarize? I don't. So perhaps it would be, I mean, the only example where one doesn't polarize is when one uses the Kosul complex. So one can try to use Kosul comps of this form and perhaps try to avoid this polarization arguments. So in our sort of operatic tool set, we have the method of Grobner basis and the Kosul duality theory. So those two bits of operatic calculus can be used to attack the problem of PBW theorems. There's another thing one can do, because again, when one writes these things in a general language, one can extrapolate them to more difficult situations. For example, I talked about operads with no differential, and Bruno, he talked about operads with differentials, the A infinity operad, the E infinity operad, the C infinity operad, the L infinity operad. Those things have differentials. So what happens there? What happens if we allow to do some kind of DG homological algebra? And the other comment that was made by Bruno is that operads are algebras themselves over a bigger operad, a bit more unwieldy object. And we can actually try to think of constructing operads as envelopes of other things I will talk about at the end. So now let me tell you about higher situations with algebra. So let me tell you how this whole PBW situation can be adapted to say something about universal envelopes in the homotopy category, if you want. So let us allow for this morphism to be a morphism of DG operads. Okay, then what does it mean to have a PBW property here? Because you see, it's kind of naive to try to imitate the definition that I had before, because now we don't identify elements up to equality, but up to quasi-iso. So how do we introduce the quasi-iso picture into here? And the correct definition is the following. So let me break this down for a second. So we had P, Q, and then I can take homology of P and homology of Q, and I have another map. So I have a map here, I have a map there. Now, there are two things that I can do in this situation. I can take an object that is a P algebra, and I can push it forward here to a Q algebra. And it will have probably a differential, and it will be a DG object, and we could compute homology, and I could do that. I could compute homology and get an HQ algebra. So that is HAV. But on the other hand, I could compute the homology of V, and I could then push it forward, right? I could do H of A, push forward H of V. And because this object here is universal, it produces a map, which is the map that I wrote here. And I will say that this alpha is derived PBW, or if you want DG PBW, whenever this natural transformation is a natural isomorphism for every P algebra V that I fed it, okay? And you will observe immediately that this condition is kind of empty if alpha and P and Q are non-DG, because then this is the identity. So I'm saying something slightly different here.
Right, so this is my question. So this is what I actually wanted to ask you. So this condition, this derived PBW is not really a derived version of previous PBW, right? So it's something different. So for example, if P and Q are not DG operads, just are classical operads, concentrated in degree 0, then it's not the same, right? So then it basically holds automatically what is written there, no?
Not quite, because the algebra V can be DG, and then I'm saying that this is exact, no? So if P and Q are, for example, associative and Lie, I can still take a DG Lie algebra, and I can wonder what the relation between this
well,
and
we
this
can
is.
assume, for example, that V it's just in degree 0 as well. It's also could be some, well, PBW, it's non-trivial statement for the case when V is concentrated in degree 0 as well, right? So.
Yes. So what I just said is that if everything is non-DG, then we just erase the H's, and this is an equality. But perhaps the point that I want to make is that even if I allow my objects to be DG, then there's a statement here that is non-trivial, which is that, for example, the PBW theorem itself implies the Quillen isomorphism here, right? And this depends on the universal envelope being exact. So if your operads are non-DG, but your objects are DG, there's already something non-trivial to say. But yeah, perhaps I didn't give a definition of what I mean by a derived analog, so perhaps yes, I'm using the word derived more freely. And the idea indeed is sort of to control this in terms of a non-DG thing. That, well, in some cases I would like to pretend that I pin down what happens with the homology of this morphism, and then it will tell me something about the homology of a push forward in the DG case. And now in the case of doing DG homological algebra, there's a notion of freeness that is the correct one, that has to do with resolving objects in DG categories in general, that is called almost-freeness. So I will say that a module is almost free if I can filter it, and you see that filtration sort of appear all the time. So if I can take the module, I can filter it, and it will become a homotopy equivalent to a free one of this shape. So a free module that is generated by cycles. Okay, it's kind of a stronger condition that being it's a strong homological condition in the sense that these things are cycles, and this is a homotopy equivalence. But this definition of being free is more or less the correct homological condition that we want to work with. And with this new definition that sort of again, this is not a definition that we gave, this is sort of something that exists in the literature, we obtained a result that has the same flavor of the classical PBW theorem. We managed to prove that if now Q is almost free as a right P module with some basis of cycles, and I want to stress cycles here, then alpha satisfies this derived PBW condition, and actually I can compute the homology of this as a functor on the homology of the original object. Okay, so it's again a sort of description of, if you want, the quasi-isomorphism type in terms of applying a functor to an object that, well, if you want to think about it in higher terms, here I sort of killed the higher operations. If this was, for example, A infinity, well, those operations in homology will be homologous to 0, right? In some sense, I forgot about a bit of the structure, and I got, well, just an isomorphism of homology, of the homology of this with the homology of that changed by some endofunctor. And the reason why we developed this is because we wanted to study envelopes of L-infinity algebras. That's the whole reason why we developed this theory, is because there was previous work by Varanovsky and by Jose Moreno Fernandez, where they tried to come up in a successful way. I mean, the word tried is perhaps they did come up with models of what L-infinity envelopes are. So I have an L-infinity algebra that I don't think was defined before, but you may know what that is. And there are many ways of producing sort of envelopes. I'll just use U upsilon because I don't want to confuse it with the other U. And these things are nice. They're good envelopes in the sense that they are equivalent to, they are homotopy equivalent to certain objects obtained from G and some A infinity structure here. But a question that one may ask, and I think, Bruno, you asked me this when I was talking about just this result like a few years ago, is, well, why don't you just use the universal envelope? Why don't you have to come up with one yourself? Why don't you just use this? And the answer is that in that case, it's difficult to compute this homology. And this theorem is built so that one can compute it. So what can we do? Again, we will use a bit of perturbation theory and show that the associated gradient of the associative operad is the Poisson infinity operad. I don't want to define that by hand. And here we can collapse com infinity to sort of a group of cycles and exhibit it as a free Lie module to the right. And what this means is that whenever I take any L-infinity algebra and compute its big universal envelope, so I take the free A-infinity algebra on G, and I declare that the higher brackets of G are the anti-symmetrization of the MK, like this, over sigma. Sorry, I don't know why I wrote lambda. Then one can actually compute the homology of this sort of monster of an algebra. And the homology is given by a symmetric algebra on the homology of the L-infinity algebra. So in particular, if G is minimal, then you just get S of G, okay, which actually was sort of guessed in the two previous models. The other thing that you can show is you can show that there's a natural map like this from the Chevalier-Alembert complex of an L-infinity algebra, and you can show that this extends the usual equivalent quasi-isomorphism, but for any L-infinity algebra. And again, this was proved by Varanovsky, for example, for his model. He showed that there's some
is B, sorry, what is B in the last formula? Yeah.
So UG is an A-infinity algebra, and B is its bar construction, if you want B infinity.
Yeah, thanks.
And yeah, and these are both DG coalgebras, yes. And finally, one can show these two models of Varanovsky and Moreno Fernandez, they're actually minimal. So they are actually infinity isomorphic. One can deduce that, and one can show that they are A infinity quasi-iso to the model that is sort of God-given. This was studied by Loday and Marco. So one can unify all the models by doing some sort of general PBW theorem in this case. Now, I think we can start finishing now, so is it an hour and 15 minutes or just an hour? I think,
normally an hour, yes.
Yeah, let's do an hour then. There's another thing that happens that, as was being mentioned by Bruno, there's a feedback loop. One can consider non-symmetric operads, and there's a non-symmetric operad controlling them. One can consider non-symmetric operads as algebras over a big operad. This is a colored operad. And one knows, coming from ideas of Gerstenhaber, that if I have an operad like this, and I sum all of this, I get a Prelli product. And then if I anti-symmetrize it, I get the famous Gerstenhaber bracket, right? So every non-symmetric operad can be made into a Prelli algebra that is weight graded by the arity, and in particular, one can exhibit operads as universal envelopes of Prelli algebras. For example, the associative operad is the universal envelope of the sort of trivially Prelli algebra whose product is 0. And the A infinity operad is the universal envelope of the resolution, of the Kosul resolution of this trivial Prelli algebra, whose relations say that the boundary of xn plus 1 is equal, sorry, I shouldn't write the bracket, I should write the Prelli product, are equal to the sum of this. So this is the Kosul model that we all know, and if I apply U to this, I get the associative infinity operad. And so this little sort of computation says, okay, it would be cool if this preserved quasi-isomorphisms, because then I am sort of resolving operads using in this case, quadratic Prelli algebras that are much simpler. This is of dimension 1, of course, and this is of dimension, well, it's well behaved in all dimensions. So an open question is, does this map satisfy the PBW property? Is it true that I have a nice description of the universal envelope of Prelli algebras? And well, I don't know. I think that the answer is that this is true. And what this means, as I was just sort of suggesting, is that we can actually exhibit operads as universal envelopes of simpler algebras, which are Prelli, and then actually try to do more of what Bruno was suggesting, some transfer, some perturbation, to actually compute the higher structure of homotopy co-operads. Okay, I mean, in the case of A infinity, the operad is actually a co-operad, but even in cases where we have quadratic linear presentation, for example, when one has, for example, the VV operad, some more complicated things can happen. So it's nice to have control over those computations. So I think I will finish now, and I will just mention that there's kind of a dual story that we studied with Ricardo Campos from Montpellier, where we try to use this sort of intuition of working with monads and resolutions and free objects to study, instead of PBW, HKR theorems, and we actually managed to obtain a dual theory for HKR results. So yes, thank you for your attention.